Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series, the section on optics and especially the chapter on diffraction. And the contents of this lecture are intensity at any point using Fresnel's half-period zones, Locarno spiral, Fresnel's integrals, and lastly Rayleigh's criterion for resolution. And we will start with Fresnel's method of determining the intensity at any point on the screen when light is coming from a source. You have got a source here, light is coming through a narrow aperture. It may be a single slit or a circular hole or an aperture, as we have seen in the previous lectures, or a thin wire or a straight edge. These are the problems we have tackled, and how these problems were discussed by Fresnel with regard to the diffraction patterns that are obtained for these problems. What was done by Fresnel was to introduce the so-called half-period zones. The idea of half-period zones were made use of by Fresnel in the wave theory of light to explain the intensity variation or to explain the patterns that we have. The patterns are, you may have interference bands, or in the case of thin wire, or you may have circular bright and dark diffraction bands or rings and so on. These are the things that we have seen. The essential point is we made use of so-called half-period zones. The plane wave front was divided into number of half-period zones. In today's lecture, the important point is, instead of this approach which is made use of by Fresnel, we will be devising an alternate method which is given the name the Locarno spiral, named after the French mathematician Marie Andrew. And so we have the Fresnel's method, where the effect at a given point due to an incident wavefront, the method consists of dividing the wavefront into half-period zones or strips. As I showed just now, the zones, the path difference between two successive zones, will be lambda by 2, which leads either to brightness or darkness. And you see in the picture here, S is a point source and P is the point where you want to find the resultant intensity. To find whether you will be having brightness at the point P or darkness at the point P, you have to find out the path difference between the beams. You got S to P and then SA from A to P. You have to essentially find the path difference, and if the path difference is integral multiple of lambda, as all of you know by now, P will be bright. If it is odd multiple of lambda by 2, the point P will be dark. So, S is a point source, okay. You have the wavefront here xy, and with reference to the point P, O is the polar wavefront, A and B are the distances separating the source and the wavefront, and B wavefront to the point P, and these are off period zones. As I told you, that is the method by which the intensities were obtained using the Fresnel's method. Now, let us see how the intensity works out to be. With P at the center and radius B, you draw the sphere touching the incident wavefront at O, you draw a sphere, okay. This is a sphere I am talking about, and the path difference between the waves traveling in the direction of SAP and SOP. Where is SAP and SOP? You have got SAP is here, yes, SAP is here, and SOP is the directory. So, between the light going straight and the other light radiation taking this route, you have got arrow here, it goes to A, and then from A to via B, it goes to P, SAP and SOP, okay. So, the path difference works out to be the path difference between the waves traveling in the direction of SAP and SOP is given by the following expression: D is equal to, D is the path difference, SA plus AP minus SOP, and that will be equal to AB. Where is AB here? You have AB here, okay. AB is the path difference between the two beams of light, the two rays of light, and so you have here, that is the path difference AB. So, this AB is also equal to MO plus ON. This is MO, you have got MO here. O is at this point. O refers to this point here, the center of the pole of the wavefront. Okay, the O is here, MO plus ON. That is your AB. Okay, AB is equal to MO plus ON, and we can do a bit of mathematics from the property of circle. MO will be AM square by 2SO. These things you can see the diagram, that AM will be H square by 2A. A is the H and HAB or what? H is the vertical height here, right? A is the distance between S and O. From O and P, the distance is B, and so you know A, B and H. Okay. Now, therefore, we express the path difference in terms of MO and ON, and MO will be equal to H square by 2A approximately. Similarly, ON will be H square by 2B, again approximation. These approximations from the property of triangles, I mean the property of circle, you have MO and ON, the values obtained are H square by 2A and H square by 2B, and so you have to sum up, that gives the path difference. That comes here, H square by 2A plus H square by 2B will be H square by 2AB into A plus B. That is the effective path difference. If AM happens to be the radius of the nth half period zone, then this path difference is equal to n lambda by 2 according to the Fresnel's method of constructing the half period zones. So, you have here the H square by 2AB into A plus B is equal to n lambda by 2. The resultant amplitude at an external point due to the wavefront can be obtained by the following method. Let us now pass on to the Locarno spiral. What is Locarno spiral? You have here, it is a complex plane. The limits of this complex plane you can have from the origin, you can go to plus 1, and you have got plus 1, similarly minus 1, similarly along the y axis also plus 1 and minus 1. I will go into the details now. Let the first half period strip of the Fresnel zones be divided into 8 substrips, and these vectors are represented from O to M1. From O to M1, this refers to the first half period zone in the complex plane. You have got a complex plane. OM1 refers to the first half period zone. Similarly, now OM2 will refer to this M1 to M2. What is M1? M1 is the displacement caused because of light passing through the first half period zone, and M2 is the displacement caused at the point P where you want to find the intensity due to light passing through the second half period zone. These things we have seen in the earlier lectures, M1, M2, M3 and so on. Okay. And now therefore, the continuous phase change is due to the continuous increase in the obliquity factor from O to M1. You know, due to the obliquity factor, M1 will be greater than M2, M2 will be greater than M3 and so on. So, the resultant amplitude at the external point due to the first half period strip is given by OM1, the OM1, that is the displacement is M1. Okay. The second will be M2. Similarly, if the process is continued, we obtain a vibration curve M1, M2. The portion M1, M2 corresponds to the second half period strip. Where is M1, M2? This is M1, M2. This shows, this vector gives the displacement that is caused at the point P due to the light coming from the second half period zone. What is the resultant displacement at the point P because of the light coming from the first half period zone and the second half period zone? The resultant will be given by OM2. So, OM2 gives the resultant displacement, which is the sum of your M1 and M2. The resultant amplitude at a point due to the first two half period strips is given by OM2, the OM2, that is your A. So, similarly, if the process is continued, we obtain the vibration curve M1, M2. The portion M1, M2 corresponds to the second half period strip. If instead of 8 substrips, if the first zone is divided into an infinite number of strips, small strips, into number of substrips of infinitesimal width, a smooth curve will be obtained that will be looking like a spiral, the so called Locarno spiral. The complete vibration curve for the whole wavefront will be a spiral as shown in the slides to come. X and Y correspond to the two extremities of the wavefront M1 and M2, refer to the edge of the first, second, etc. of period strips. Similarly, M1 and M2 prime refer to the edge of the first, second, etc. of period strips of the lower portion of the wavefront. You have got the upper portion, lower portion. So, the so called spiral which I am showing now, the so called the Locarno spiral will be looking like this. So, you have got the x axis. As I told you, the limits will be +1, -1 here. This is a complex plane, and along the y axis is a +1, -1. This is a graphical method of determining the intensity at any given point using what we call as Locarno spirals. So, whatever we had earlier, as I told you, if the first half period zone is divided into number of substrips, so instead of straight lines, we will be having this kind of curved things. So, your M1 will be here, M1 we saw earlier, M2 we saw earlier, the amplitudes obtained at the point P due to the first zone, M2 is the amplitude obtained due to the light coming through the second zone and so on. So, we pass on to now the Locarno spiral. This is a so called Locarno spiral which I showed, named after Marie Alfred Carnot, a French mathematician. The characteristic of this curve is that at any point P on the curve, the phase lag delta is directly proportional to the square of the distance V. I will show you in a minute what I mean by distance V and the displacement, etc. The distance is measured along the length of the curve from the point O. This is the delta is the phase difference, and the vibration curve, this is the thing what I am talking about. There is a V here, the V is here along this direction, and delta is the amplitude. Okay. Therefore, we go through the mathematical steps here, namely for a path difference of lambda, the phase difference of 2 pi, that is very well known. Hence, for a path difference of d, this is the d that we calculated earlier. The phase difference will be given by delta, that delta will be 2 pi by lambda into d. We will have a short break at this point. Welcome back to the break. I have been telling you about the phase difference delta, which I showed in the picture here, the phase difference delta can be given by an expression of this kind. Delta will be 2 pi by lambda, that of course you know how it comes, into d the path difference, the value of which we obtained earlier. So, now you substitute your d here, the value that you got earlier. So, your delta, the phase difference will be pi by 2 into 2h square into a plus b by a b into lambda. So, that works out to be pi by 2 into v square. The value of v is given by v square is equal to 2h square into a plus b by a b into lambda. Then v square is also now getting reduced to h multiplied by square root of 2 into a plus b by a b into lambda. The Locarno spiral can be used for any diffraction problem irrespective of the value of a, b and lambda. You can have a, b and lambda, you know the distances separating the object and the wavefront and the point P, and lambda is the wavelength of the light used, and so on. So, irrespective of a, b and lambda, this methodology that is adopted can be used to study any diffraction problem, and again it may be straight edge or a circular aperture, whatever be the obstacle that comes in the path of the light beam for which you want to get the diffraction pattern. The Locarno spiral method can be effectively be applied. The Locarno spiral, as I told you earlier, is a spiral in a complex plane. Again, as I told you earlier, the limits are +1 to -1 in both axes, x and y axis. It depends on dimensionless variable v, which in turn depends on the arc length of the wavefront p as shown in the figure. In the figure, we have the vertical length. It is named after Marie Alfred Locarno, the French mathematician who applied this method to all Fresnel diffraction problems. For any point on the Locarno spiral, the x and y coordinates are given by two integrals. You know the coordinates are given by two integrals named after Fresnel, the Fresnel's integrals. Let us consider the point P on the spiral. The distance of the point P along the curve from the origin is v. The tangent to the curve at P makes an angle delta with respect to the x axis. This is the delta and this is the point P. This is the Fresnel's the Locarno spiral. Okay. The Fresnel's integrals are given as follows now. Lambda corresponds to the phase change from O to P. Phase change from O to P, this is the phase difference, right? For a small displacement dv of the point along the corresponding changes in the coordinates of the point be dx and dy. You know, along this in the xy plane, for a small displacement dv, the points, the coordinates are dx and dy. Then dx will be equal to dv into cos delta and dy will be dv into sin delta. So, we come across what are called Fresnel's integrals, which go like this. The expressions for the Fresnel's integrals are dx is equal to cos into pi v square by 2 into 2v, and your dy will be given as sin into pi v square by 2 into dv. So, the Fresnel's integrals are again given as x is equal to integral of dx. The integral of dx is nothing but 0 to v. What is v? V is dimensionless constant which is related to your h. So, that will be equal to cos into pi v square by 2 into 2v, and y is nothing but integral of dy, again that is integral of 0 to v into sin into pi v square by 2 into dv. These are called Fresnel's integrals. Nowadays, with the advancement of computational techniques, it is easier to evaluate the Fresnel's integrals rather than going through deeply into the Locarno spiral. Still, the Locarno spiral, it gives you a pictorial representation of the way in which the displacements are shown or exhibited, but the point is with the advancement of computation techniques, it is easier to evaluate the Fresnel's integrals, and the intensity distribution at any point on the screen, irrespective of the fact whether you have a straight edge or a aperture or an circular aperture or a rectangular aperture or a single slit or an obstacle, a circular obstacle, the pattern that you obtain, we have studied these patterns using the Fresnel's method, by constructing. How did we obtain? By constructing what are called half period zones. That is the approach that we have made in the earlier lectures to explain the kind of diffraction pattern that you obtain in the cases which I mentioned earlier. Instead of constructing half period zones, the Locarno spiral approach is another approach by which one can study the same diffraction patterns. So, it is a different technique altogether, and the Locarno spiral, Fresnel's integrals, they go hand in hand, they are related, and one can evaluate Fresnel's integrals and obtain the intensity distribution and thereby explain the diffraction patterns obtained for the different cases. What is meant by resolution or resolving power? One has to start with resolving power. It is the ability of the human eye or a telescope or microscope to see the two objects which are close to each other, whether they are seen as two distinct objects or they are seen as a single object, whether the images overlap or whether they are clearly seen. That is what we mean by the resolving power. You talk of resolution, resolving, that is the objects to be resolved, to be seen distinctly as two different objects or three different objects. So, that is the resolving power. When two objects or their images are very close to each other, they appear as one. If they are very close, obviously they will be appearing as one, and it is not possible for the eye to see them as separate entities. If the objects are not seen separately, then we say the details are not resolved by the human eye. Optical instruments are used to assist the eye in resolving the objects or images. Now, supposing in the College of Engineering, Guindy, you have the clock tower where, supposing you place 5 candles, and I see from this building, I can see all the 5 candles or all the 5 tube lights or bulbs which are kept on the top of the clock tower as 5 distinct objects. Suppose I move through a distance 1 kilometer or a few kilometers, 2 kilometers, whether we can see the 5 bulbs separately by the human eye. It is not possible. Then you have to use some optical instrument so that you see the 5 bulbs or tube lights as 5 independent entities. The human eye cannot resolve. The methods adopted to seeing the close objects as separate objects is called as resolution. The ability of an optical instrument to produce distinctly separate images of 2 objects located very close to each other is called the resolving power. The ability to resolve. The Americans have got their optical equipment fitted to the spy satellites. The satellites are capable of having very high resolution and are capable of seeing the movement of even tiny objects, whereas other countries, maybe India, can see a army tank, a military tank, whereas the movement of tiny things cannot be seen. So, such high resolving power instruments are required to see the movement of objects or movement of even a single person or a terrorist can be seen by an equipment or an optical instrument which has got a very high resolving power. That is how you look at some enemy or a terrorist, so that he is killed or captured and so on. So, resolving power is normally defined as the reciprocal of the smallest angle subtended at the objective of the optical instrument by 2 point objects, which can be distinguished as separate. Let us now see the objects in visual space. There is the intensity caused by one of the sources. You got two sources. You have a hump light coming from the first object. The second hump is the light coming from the second object. Now you come across what is called Rayleigh's criterion. Rayleigh gave a criterion, even though it is ad hoc. He said that two objects can be seen as two distinct objects only if the hump and you see the criterion states 2 point or lines are just resolved. The peak of the point spread function lies on the first trough. This is the first trough, right? The first trough should coincide with the first crust. You got the crust here, trough here, right? First trough of the first source should coincide with the crust of the light coming from the second source. If these two are closer to each other, suppose the trough, suppose this crust comes closer, then it cannot be resolved. If they are far away, supposing the second is far away, then they will be perfectly resolved. The minimum resolution, the things to be seen as two distinct objects, is the minimum of the first should coincide with the maximum of the second. The light coming from the first object, light coming from the second object. So, the important point is the minimum of the first should coincide with the maximum of the second. Okay. So, you have the minimum, and the minimum is here and the maximum is here. They should coincide. On the other hand, if they come closer, then the resolution will be lost. They will be observed as two, not as two distinct objects. Okay. You have got two distinct objects. Okay. When they are, the humps are separated by a large distance, they are seen as two independent entities. They are resolved. Here you have got the just resolution. Here there is no resolution at all. Therefore, the objects in visual space, the Rayleigh criterion states that two sources are just resolved. The central maximum, right? You have the central maximum and this is the minimum. The central maximum of the diffraction pattern of one of the source falls on the first minimum of the other. This is one thing, right? This is the central maximum, the minimum here. This minimum should coincide with the maximum of the second source. This is the first source, light coming from the first source, the light coming from the second source. The first minimum of the light coming from the first source should coincide with the maximum of the light coming from the second source. This is the just condition for the minimum thing for resolution. These two are separated far away, as shown earlier. They will be well resolved. So, now you have got well resolved image like this. They just resolved, not resolved at all. Okay. So, the Rayleigh's criterion says when a beam of light from a point object passes through the objective of the telescope, the lens acts like a circular aperture and produces a diffraction pattern in a point image. This diffraction pattern is a bright disk surrounded by alternate bright and dark rings. So, light coming through a circular aperture will give rise to bright and dark rings. It is called a Airy's disk. Let me now summarize as what we have seen from this lecture. The intensity at any point can be obtained from Locarno spiral. So, Locarno spiral can be used for any diffraction problem. Any point on the spiral depends upon Fresnel's integrals. And lastly, Rayleigh's criterion for resolution was explained. We will go to the question session. The questions are: What do you understand by Locarno spiral? X-plane Fresnel's integrals. X-plane Rayleigh's criterion for resolution. With this, we come to the end of this lecture, and in the lecture to come, we will see the last section on holography. Thank you.